We are good to go. So the floor is yours, Christoph.
Thank you very much, Dennis. So hello, everyone. I will show you an overview of what we have been doing in terms of CI/CD using GitHub on the pilot application urban building of the COE Hidalgo 2. To start with, for those of you who don't know about Hidalgo 2, we are a few partners from several countries working on different aspects of the COE, and Strasbourg is involved as a use case owner, as a few other partners. And in the project, we are working on one of the four pilot applications on urban building energy simulation from a single building to a full city. I will show you a video at the end so that you see what is going on with it. So I will show you maybe a few, like the general objective of the pilot, one slide, and the general workflow of the pilot to show the complexity of the application. And then I will try to explain what we have been doing in terms of CI/CD, and that we call now HPC Ops, if that's okay with you. And then a quick video and some conclusion. So what we are doing here is to provide some building energy simulation tools in order to help with energy savings, considering the fact that buildings have a huge impact on greenhouse gases emission and also energy consumption. So we wish to, at the European level, to reduce that impact tremendously. For example, in France, up to 700,000 renovation per year. To do so, we require having access to simulation tools in order to assess the energy consumption and also green gas emission on buildings. So we are developing models from the building scale up to the urban scale and possibly beyond on very large metropoles or maybe several cities. So we take care of energy consumption, thermal comfort, indoor air quality in our models. One aspect is that we have a strong link with another pilot, which is urban air pollution models that will provide the actually the external or the outdoor air quality simulation application, as well as transport of the heat transfer within the air. So there will be a strong coupling between those two pilots. In terms of workflow, here's an overview, relatively detailed overview of the workflow that is going on. I won't go into the details or explanations here, just that you will see in the application that we start at the top left where my cursor is, where we define a location. And then from this location, we retrieve various data from the web and then generate meshes, which are then partitioned, and then we deploy on simulators, on HPC systems, our simulations, and then we recover the results. It's an ongoing work. It's a 1-year-old project now, and we will work on this for the next 3 years. So regarding CI/CD, maybe let's start with the urban building software stack. We build on software called Field++ that we developed in Strasbourg. It's an open source software. You have access to it here. We have several tools for simulations available or libraries available. You see on the right an image showing what is contained in this library or in this framework. So it's a C++ code using C++17 and now it's also compatible with 20. It's currently MPI based using Boost, PESI, Python. So we actually depend on a lot of software, and those software have also dependencies. And in order to take care of the complexity of PhilPP, we have set up an environment using GitHub with GitHub Actions. So if I click here on the link, I don't know if the slides will be available to you afterwards, but that's okay with me with distributing them. You see here various workflows that are available here for various tasks. Not all are very important. Maybe the most important one is this one where we check that everything is all right. This one here failed because there was an issue with uploading the Docker, some Docker image. So in order to deal with Phil++ complexity, we have set up, as I said, a complex environment, which I will show you in a few seconds. And the software, our framework, is strongly based on the generation of Docker images. We use Docker and also Singularity, but mainly Docker to start with. And we generate images on various systems in order to check, let's say, the robustness of the code on various systems. The urban building software stacks also highly depends on Python. Well, Phil++ also depends on Python, but we have maybe a few important tools also written explicitly for the urban building stack. And we use also Modelica as a modeling language, and we generate from this modeling language FMUs for the building models that are distributed in parallel on the HPC systems. So let's see what's going on with Phil++ standard DevOps. So here, this is, I guess, a standard system for you, maybe regarding continuous integration. For Phil++, as I said, we have important dependencies, or quite a few dependencies. And what we do is that we set Docker images using continuous integration to have the Phil++ environment ready for various systems. You see them here from Ubuntu to Debian and SPAC. We have two flavors for SPAC, one based on OpenMPI, the other one on MPitch, depending on the system that we deploy afterwards our application. Then from these images that are ready to compile Phil++, then we can have the pipeline triggered from pull request or merge, or from the GUI of the GitHub Action. So by hand, we can actually trigger the pipeline, or using scheduling. So GitHub Action supports cron-like systems. And so we have mainly three continuous integration systems being launched whenever we have a pull request or a merge, which is Ubuntu 22, Ubuntu 24 now, and Debian 12. And regarding the older Ubuntu 20 or SPAC, they are built using the scheduled system. At the end of different stages of the build, we upload Docker images, which are generated automatically from this continuous integration. We upload the Docker images on the GitHub container registry for the initially, the Docker images were also for the environment were also on GSCR.io. And if this is successful, we build also Aptainer images. Alors, we don't build Aptainer images for all the systems here, mainly for Ubuntu and SPAC and Pitch, which are the main two systems that we use on your HPC. Using Docker or Aptainer, then we develop our projects or application. We have several large projects with Phil++, which are using these tools to develop further in advanced applications. Okay. Now we start from the Aptainer images, which were built at this level. And upon success of the generation of these images, we launch large-scale benchmarking. So this so-called HPC ops use Reframe, again, GitHub Action, and currently we have been using only Slurm. That's what we find on either on our local HPC system, on the EuroHPC system, or also we have access to Polish HPC systems through Hidalgo 2. If actually Eagle should not be green, in the sense that there is currently we have currently an issue on Eagle, but not because they use quite old libc libraries, so we have some issues currently with Eagle. But anyway, on the other system, whenever it's green, that means that it's fully working. And so this HPC of system, we have developed it also for the urban building CI/CD system. So we start from the standard CI/CD. So whenever we develop our application and we have pull request or we have merge, then we build the code, we build some packages, we build from these packages Docker images. If this is successful, then we build Aptainer images. Both Docker and Aptainer images are uploaded on the container registry from GitHub. If we have releases, then we have also a release system put in place. Now, if the Aptainer image is successful, then we go to the HPC of system. And in that case, you see here, I will click on this part of, in a few seconds, I will click here to show you what's going on in GitHub. So we have an event, we have an event that triggers the pipeline whenever the Aptainer images have been successfully built. And this event triggers build depending on messages. We have a small language embedded in the commit messages of our software. We have a small language that can allow us to enable or skip machines. So for example, by default, we can run on all the machines, but we can skip some selected machines, skip all machines except one, things like that. So we can easily, the developer can easily actually select a machine to be run on or and to skip other easily. By default, what we have set is that we have relatively small tests on 128 cores that are running by default through the CI/CD system. The larger tests are run either by hand, so we use the GUI in order to trigger the test, or a scheduled test through cron-like system using GitHub in order to run large tests. They are not run by default whenever we have a pull request or merge or something like that. We use Reframe as a regression framework for the performance and check that the performance are okay. And we deploy the performance reports automatically on the GitHub of the Git repositories of the COE, which is currently a Bitbucket repository, as well as on our data system here in Strasbourg. So if I click here on an execution of framework, so you see this one has been run, I think it was run today. You see here the pipeline execution. So for us, dataset factory is it's actually not very important in the case of the benchmark. We have here set one benchmark that is being run. So it defines a dataset to be downloaded and provided then to the HPC system. We check the singularity image existence. We have had some issues in the past that, or some bugs, and in order to debug, I added a way to verify. So it's very simple, relatively simple check that verifies that an image is actually available on GHCR.io. So for example, what it means here is that I told you about a language available in the commit messages of our system. A developer that works in a branch can tell the system to actually run the CI/CD for the specific branch. By default, we don't do it. We do it only for the main branch. But once we reach the end of the development and we want to verify that the HPC ops are running fine, we can tell the system that to actually run on the larger runs. And so in that case, maybe you see here, we have here the image and we have here the tag. Here we run in the master branch, but if we were in another branch, then we would see it here and the system would check that the singularity image is indeed available. And then we check that the runners at the beginning, so you see here, we check that the runners are available. So Gaia is our own system. Lumi runner is a runner which is on Lumi, Meluxina, Discover. Currently, Eagle is not working, and we have not put Carolina here because it takes tremendous amount of time to run on Carolina. The queues are extremely long, and so we don't use it in our CI/CD currently. We can run on Carolina by hand, but not in the automated CI/CD. So once we have checked that the runners are available, I have built here the HPC system factory, that is to say the the runners where we are going to run our applications. And so here you see that we run on all these machines. So you see there is a difference of time here. It's due to the fact that we have a queuing system. And so, for example, on Discover and Meluxina, it runs extremely fast, usually. Whereas on Lumi or Gaia, which is quite used, then sometimes we have to wait a little bit to have our code being run. Once the software is being run and we get the reports, and we deploy the reports either on the Bitbucket of the COE, because our colleagues from the COE would like to have access to these reports, and we also push the reports of each machine on our local system. So here, in our application, the post-processing is done afterwards, and we retrieve the data from this stage here. Okay, so let's go back. So now I'm going to show you a video of an execution of the application in, let's say, a manual way. So in our application, what we do is that we set a location of a city. So here it's the city of Luxembourg. We set an area around the city, so 4 kilometers square around the city. And here you see it's a little bit accelerated, so maybe I'm going to slow it a little bit down. And here, maybe I stop. Here on the left, you see that in our application, we can select, maybe I go back a little bit, yes. We can select the different machines on which to run. So here, my colleague who made the video selected Discoverer, the partition on which we want to execute, and then some account information, the number of nodes, is going to enter that now. And so it's 5 nodes and 128 cores. And then the time setting, so I think he sets up for 2 months simulation here with a certain time step. And then when he clicks on the run button, so we are not really in a benchmark, we are no more in a benchmark framework. We are in a simulation framework, so we use also the CI/CD in order to trigger jobs. So you see the execution here. The execution that you see is basically, we call several times Singularity, or our application from Singularity, to download the data, to execute the workflow that I showed you at the beginning. So there are several calls to Singularity in order to retrieve the data set, to retrieve some simulation plugins, and then at the end to execute the framework, and then the results from Reframe were shown earlier. And now we can have access to the download here. So if I go in the CI here, all workflows, so you see here CI is a workflow for, is a GitHub workflow for the developers, and simulates, but we use it for our application in order to execute our application, for a simulation from our application. And so we use the full capabilities of the GitHub action system. If I look here, for those of you who are familiar with it, so for example, for simulate, you see here a part of the code that is being used. So a GitHub action workflow is written in YAML format. So we can trigger the simulate framework, the simulate workflow either from another repository using this, or using so-called workflow dispatch, which is a very powerful system which allows us either to call the workflow using the GitHub Action API, or to actually execute the workflow using a very simple graphical interface. So if I click here on simulate, you see here a button, and I can execute, for example, on Meluxina here 2 nodes. So it's very primitive, but for a developer, it's quite useful because it allows us to check that things are okay. So here I can run the workflow, and running the workflow means that I executed the YAML file earlier. So you see now it starts. It does the initial checks for the dataset and for the HPC system. Here there is a default dataset that we put. And if I click here on Meluxina, now you see it runs on Meluxina so first it logs on the logging 03 of Meluxina, so there are several login nodes. And then it does a checkout of the repository, it installs some dependencies. And yes, I forgot to talk about that. On the HPC system, sometimes, for example, it's not possible to use Singularity. It's not possible to use Singularity on the login nodes. Or even, it's not the reframe version, the Python version on the login nodes is very old, and it's not possible to run reframe on the login nodes. And so what we do in that case is that we have three ways to execute, depending on the machine. We have 3 ways to execute our workflows. On Meluxina, what we can do is that we can use the Slurm REST API in order to trigger the job. It's very convenient. So we use Slurm in order to execute the Slurm API in order to execute our workflow. So you see the execution here, and at the end, it runs on 128 tasks per node and 2 nodes here. That's it. And you have and then the upload of the results. So this is one way to do it using the Slurm REST API, because it's not possible to use Singularity on Meluxina. But I think Meluxina is the only HPC system which has installed the Slurm REST API. On the other system, so you see how the code looks like. So we do a few checks. No, I want to show you for simulate. So here we select the machine. We use a GitHub script in order to select the machine on which we want to run. We have the dataset factory here that checked the dataset, and then we have a default dataset in case the user has not given a dataset. Provide some outputs, and then we launch the simulation. And here you see we have several variables that are defined. And depending on the machine, so if the machine supports REST API, then we use REST API, and this is the way it is being executed with various options. Then otherwise, we use the command line interface. So in that case, it means that we can run reframe and singularity on the login nodes. So this is a convenient case. And the last case, we don't have Slurm REST API, and it's not possible to run Singularity, or we have a Python version which is too old, so we have to actually use sbatch. So reframe will be executed through a Slurm job, and which will then trigger other Slurm jobs for the simulation that we need to run. And we have a monitoring system that allows to follow what is going on. So we have a logging system that nicely shows in GitHub Action how the code is going on, is being executed, even though we run into sbatch. And you see here the downloading and the way we use our code. The CI is very similar, except that we are more like in a benchmark mode. It's a bit more involved in the sense that here we don't run on one machine, but we run on several machines. So for example, here, this step here, which is called check runner, verifies that the runner is actually available, that it's running on the HPC system or on our own system. So it verifies that. And once it's done in the factory, we look into the commit messages in order to check what we have to do. And we have some logic which allows to skip or to enable some one machine or several machines. And depending on that, we include in a simulation matrix the machine that needs to be used for the benchmark. So you have here some examples of what we have been doing. And then I think there is no time to show how reframe works here. But we use reframe to then execute the benchmark and configure different Slurm jobs to check the performances on different setup of the simulation. So I'm almost done here. So what we have been doing, so now we have a pipeline which is automated, fully integrated with container updates. So as you have seen that we start from Field++, so we generate the Field++ containers. From these Field++ containers, we create the containers for urban building. And if it's all successful, then we do the benchmarking on the HPC system, both for Field++, but also for urban building. On our to-do list, we still need to do some automating. And one aspect of the automation, so we have here just a mock-up. It was a proof of concept for us. We would like to have a website that not only shows here the reframe reports I've done at several times. So I did that back in December, I think. But here we will have a website which is updated automatically depending on the reframe reports that have been generated. And not only it shows the benchmark per machines, but it will show also the performance evolution over time, depending on the benchmark and depending on the machines. So this is something which is not yet done. It's someone is actually working on it currently. We have some people working on it, and we hope to be able to show this at the next General Assembly of the COE, Hidalgo 2, beginning of June. But this is the kind of thing that we would like to automatically generate and verify that the performance are good, and that we see over time that the performance are kept or even are improved. There are some HPC systems which are not yet available, so we are also working on this, and we have a colleague from the COE, Samir, who's working on the GitLab port of the GitHub system. One aspect here which is important is that we generate actually quite a bit of data, and we have not fully let's say we have not found yet a good sustainable data management system. At some point, we will need to have some of the data that we generate and that we store to become obsolete or to be archived. So we have to think about how we deal with all the data we accumulate now from all the simulation. And so it's not yet clear for us what we are going to do. We will have probably a first version of this for the beginning of June for the General Assembly of the COE. I'm done with the presentation.